All right. Exam 2 is a week from today. Monday the 10th. My anniversary. I know, it's going to be romantic. This test is going to be so romantic. And the topics are going to be, well, first it's cumulative. And then second, the new stuff that's going to be on it is vector-related stuff and 2D kinematics, and that's all. Okay, so Wednesday, feel free to come with questions about 2D kinematics or vector stuff if any of the practice problems aren't making sense, and I'd be happy to spend time on those. Today, at least for quite a while, we'll do most of the class just doing example problems in 2D kinematics. Anybody have any questions before I start with that? Yeah?
So when you say cumulative, are you going to have actual problems with stuff from the first test, or are you going to have like the concepts?
No, actual questions like the previous practice problems. So you should spend some time at least going back and looking back at those problems. I think the way I would recommend doing it is look back at those problems and just ask yourself, do I know how to do this? And if you can sort of think like, okay, you do this and this and this and this, then move on to the next one. And then spend the time working through the problems that where you're like, you know, you can't think how to do it, you know. Any other questions about the test or about practice problems? All right. So let's do this example. Remember, we spent a bit of time on this idea that if you shoot a gun horizontally and you drop a bullet at the same time, they hit the ground at the same time. We watched the video, and then I think we did a problem related to that, right? And we spent a bit of time on it because it's sort of counterintuitive. So now what we're going to do is we're going to do the same thing again, but this time the gun is going to be angled up a very small amount, you know. So we're going to start with the gun angled up at 1 degree, just 1 degree above horizontal. And intuitively, can you imagine what's that going to do to the amount of time it takes for the bullet to hit the ground? What? It's going to increase it. And because a bullet is going so fast, it's going to increase it a pretty significant amount, even though 1 degree is barely even visible, you know. So so we're going to revisit bullet being dropped and fired. I'm going to spend most of the class drawing this picture. Okay, so this time, I didn't finish this guy. This is like, doesn't it look like like the nightmare of like the doula. Like someone who's like a doula has this nightmare where he's back to back with a guy with a gun and he's just holding this bullet. So this time the gun shoots the bullet at an angle of 1 degree. And let's say that the height that they're dropped and shot from is 1.5 meters. And the idea, not to give away the punchline, is the 1 degree angle will have a big effect on the time that it takes to hit the ground. Okay, so the first one we're going to do is how long does the dropped bullet take to hit the ground? Okay, so take a few minutes and work together on that one. Come up with a time for that, and when you're done working on it, I'll go through it. Let's go through this one. So first we're dealing with the dropped one. We're going to start with making these 4 choices. Time equals 0 is the instant that it's dropped. Time final is the instant it hits the ground. And then I'm going to choose the origin and the coordinate system in a way that's pretty similar to how I usually do it. I'm going to put the origin on the ground beneath where the object is at time equals 0, and y-axis up, and then x-axis, well, it doesn't even matter because the thing isn't moving horizontally, but we can think of it like this. So the origin is on the ground beneath the drop. And the coordinate system has the y-axis up and the x-axis horizontal. Do we know time final? No, that's what we're looking for. Do we know acceleration? Yep, so ax is 0, ay is negative 9.81. Do we know pix? 0, yep. And please stop me if you have any questions about any of this. PIY, what's that? Yep, positive 1.5. PFX? Yeah, we're that's sort of assuming that it's not going to drift off. We'll leave it off. Let's not make any assumptions about what's going to happen to the motion. But we do know that PFY has to be equal to 0. That's what it means to hit the ground. Do we know anything about VI? So what's VIX? 0. And what's VIY? Yep. Because it's dropped, and so the velocity when it's dropped is the same as what it's dropped from. And do we know anything about the final velocity? No. And so based on this, the equation that we're going to use is PFY is equal to PIY plus VIYTF plus 1/2 ay tf squared. So 0 is equal to 1.5 minus 4.905 tf squared. So 4.905 tf squared is 1.5. And then tf squared is 1.5 divided by 4.905. Take the square root of that, and what do you get for tf? What is it? 0.55. And the square root means there's a plus or minus. Which one do we want? Positive, because it's time. That's easy. Okay, so 0.55 seconds.
So since it was dropped, we know that the velocity initial for both is 0 because it's just
Yeah, so the initial velocity, if something's dropped, the initial velocity is the same as what it's dropped from. So if it's a helicopter, it has the helicopter's velocity. If it's a car, it has the car's velocity. And in this case, it's dropped from the ground, so it has the ground's velocity, which is 0. Okay, so now part B. How long does it take the bullet to hit the ground? Yeah, they're both bullets. Okay, if the gun was horizontal, how long would it take to hit the ground? 0.55. Yep. Okay, so we're going to calculate now with the 1 degree angle. So first we'll make choose these 4 things. Time equals 0 is the instant that it's shot. Time final is when it hits the ground. And I'll choose the origin and the coordinate system orientation the same way that I did for the other one. So we'll put the origin on the ground, y-axis up, the x-axis horizontal in the direction that the bullet's going. Well, really, the way I drew that coordinate system, it's not in free fall until it leaves the muzzle. So so the origin is on the ground beneath where it's fired. And the coordinate system has the y-axis up and the x-axis horizontal in the direction of motion. We're trying to find time final. The acceleration we know because it's free fall. The initial position, what's PIX? 0. What's PIY? Yep. What do we know about P final? We know the y component is 0. We don't know anything about the x component. That's some big positive number. We don't know what that is, but we can live without it if we can find TF. Initial velocity. We know both of these, and we can get them from the fact that we know the speed is 500, and the angle, the counterclockwise angle from the positive x-axis to the velocity vector. So I'll draw the coordinate system like this. The initial velocity vector looks like this with a length of 500, and this angle is 1 degree. So this initial velocity vector is 500 times the cosine of 1 degree, 500 times the sine of 1 degree. So what do you get for VIX? 499.9. So, okay, so that's very close to 500. Basically, all of that speed of 500 is acting horizontally. And then what do you get for the y component? 8.73. And then do we know anything about the final velocity? No. All right, so the equation that should work with this is the same one that worked in part A. So PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. Bless you. So 0 is equal to 1.5 plus 8.73 TF minus 4.905 TF squared. You can do this with the quadratic formula. So this is A, this is B, and this is C. And if you solve that, what do you get for TF? What are the two roots? Negative 1.57?
0.157.
1.157?
No, just negative 0.157.
0.157. Okay, and we want the positive one, so not that one. All right, so the difference was between 0.55 seconds and 1.94 seconds. There was one value in the list of things that we knew that changed, that this depended on. Well, there were two things that changed, but only one of them affected the answer. What variable was that affected this answer? It was the initial velocity vector, and it was only one of those components that came into this. It was just the y component. And notice that that y component depends on how fast the thing's going. So even though this was a tiny angle, 1 degree, because the bullet's going really fast, vertically what you had effectively was like this bullet being thrown up into the air at 20 miles per hour. You know, that's a tiny part of 500 of over 1,000 miles per hour is how fast the bullet's moving, but it's enough to make a big difference in the amount of time. What would happen if you shot a bullet 1 degree below horizontal? What would happen to the time? Yeah, it would be a much shorter time than 0.55 seconds, again because of that vertical component of the initial velocity. Okay, one more part of this. So part C, how far away horizontally does the bullet hit? So for this one, those four things, we can keep those the same. And if we keep those the same, then everything we knew before stays the same. So we still know, well, we still know all the stuff from before. All the stuff from part B. And now we also know that time final is, what was it, 1.94? And we're trying to calculate PFX. So we can use this equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 499.9 times 1.94 plus 0 because AX is equal to 0. And what do you get for that? 969.8 meters, 1,000 meters, so over half a mile away. Yes?
So does A, the acceleration equals 0?
Yes. The x component of acceleration is always equal to 0, the horizontal part. The y component is the one that's always negative 9.81. So since we were using the x equation, we used the 0 there.
Isn't it accelerating?
It is, if you ignore air resistance, it's not accelerating. The x component of the velocity is staying exactly the same. So that sort of brings up the next thing I wanted to ask. So we did 3 calculations. We did the calculation of the time for the bullet that's dropped, the calculation of the time for the bullet that's shot at the low angle, and then how far away horizontally the bullet landed. One of those 3 things, this free fall approximation where we assume there's no air resistance, gives a really bad result. 2 of them, it gives really good results. So what do you think is the bad one? The third one, that distance would be off drastically. I'm not sure how much, but by a large percentage. So can you think of why that would be? So the first 2 are fine because all we're looking at is vertical things, and it never has a big vertical speed. And remember, the horizontal stuff happens independently of the vertical stuff. So when the bullet's just dropped, it never gets going very fast. Even when it's shot at the 1-degree angle, vertically it never has a very big speed, and so air resistance is pretty small. But when you look at the horizontal motion, and horizontally the component of the velocity is 500 meters per second almost, air resistance has a huge effect on the motion. And so if you're ever, when you're trying to figure out when air resistance is affecting a problem, breaking it up into an air resistance effect on the horizontal part versus the vertical part is sort of a sensible way to think about it. We're not going to do that for calculations, but just for sort of making sense out of the world or whatever. Okay, let me do one example. All the examples that we've done are in free fall. So how about one that's not in free fall? And this is, the one I'm going to do here is pretty similar to number 1 from the two-dimensional kinematics problems. So let's just say, I'm not going to draw a picture, but let's say an object starts with a velocity vector of 30, negative 20 meters per second. And moves with a constant acceleration of negative 10, negative 5 meters per second squared. What's the object's displacement over 5 seconds? Okay, so the first thing we always do is make these 4 choices. Time equals 0 is going to be the start of the motion. I'll say when the velocity is 30, negative 20. And time final is going to be 5 seconds. So 5 seconds go by. The origin and the coordinate system, though, this one's different than the other ones. And the reason it's different is that we already have things in terms of components. And, bless you, remember that in the vector problems, in order to come up with the components, we had to know what the coordinate system was. And so these things are already, well, at least the coordinate system orientation already has to be defined for us to have this in components. So this is like already chosen. Because we're given components. Velocity and acceleration components. The origin, let's put that at the object's location when time is equal to 0. Okay, so do we know time final? Yep. That's 5 seconds. Do we know anything about the acceleration? Yep, that's given. So AX is negative 10. AY is negative 5. Do we know anything about the initial position? Yep, we defined it as 0, 0 when we put our origin at the object's location at time equals 0. That is the meaning of initial position. So PIX is 0, PIY is 0. VIX is given. That's 30. VIY is given. That's negative 20. And we're trying to calculate, I guess I skipped over the P final, but we're trying to calculate PFX and PFY. We can just do them one at a time. Let's do PFX first. So PFX is equal to PIX plus VIX T final plus 1/2 AX TF squared. So PFX is equal to 0 plus 30 times 5 plus 1/2 times negative 10 times 5 squared. So this one's negative 125. This one's positive 150. And so PFX is positive 25 meters. And then for PFY, we'll use the same equation, just the Y version. So PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So PFY is equal to 0 plus negative 20 times 5 plus 1/2 times negative 5 times 5 squared. Bless you. So this is negative 62.5. This is negative 100. So PFY is negative 162.5 meters. Okay, so the displacement now, we want the displacement from the starting point to the ending point. Yes?
So if I were to see a negative 162.5, I would feel like I did something wrong. Because it's like,
Oh,
why?
so what does that mean? So what that means is just that the object started here, and after the 5 seconds, it ended up positive 25, negative 162.5. So whatever the motion looked like, it started here and ended here. So yeah, positions and velocities and accelerations, the signs are just part of the direction. Time is the only one that can't be negative. Okay, so the displacement is the position at the later instant minus the position at the earlier instant. At the later instant, the position is 25, negative 162.5. At the earlier instant, it was at the origin. And so the displacement just ends up being, in this case, the final position, 25, negative 162.5 meters. That's right. I just want the vector components. So remember that in 1D motion, displacement was a directional quantity, and it's the same here, so it's a vector. So I want it as components. Okay. So you just have to subtract vector components to get it of positions. Any other questions about that one? Okay, there's one more thing I want to say before. So this is the end of 2D kinematics of particles. Like I said, if you bring problems you want me to do on Wednesday, I'd be happy to do that. But otherwise, I'm going to go on to the next stuff. But this is sort of intuitive, an intuitive understanding of acceleration in 2 dimensions. So the first thing to remember is that acceleration measures change in velocity. So in 1D, like motion along a line, or 2D, or 3D, we're not doing those kind of problems, but if the object's velocity stays constant, the acceleration is 0. Okay, so what about non-zero acceleration? In 1 dimension, non-zero acceleration only changes speed. And, you know, we've talked about this a lot. If the velocity and the acceleration have the same sign, the object is speeding up. And if velocity and acceleration have opposite signs, the object's slowing down. In 2D, there's something new that acceleration can do. It leads to changing speed, and it also causes turning, makes the object turn. So to visualize the acceleration of a motion in 2 dimensions, first, draw the object's velocity vector. The velocity vector is always tangent to the path of motion. second is to draw the parallel part of the acceleration. I'm going to call that A parallel, and it's a vector. And so to draw this, if the object is speeding up, A parallel is parallel to the velocity in the same direction as the velocity. If the object is slowing down, it's parallel to the velocity and in the opposite direction. Then the third step is to draw the perpendicular part of the acceleration. I'll call that A perpendicular. And A perpendicular is perpendicular to the velocity vector in the direction the object is turning. And then the last step is use the rules of vector addition for the total acceleration vector, and that so the total acceleration vector is equal to the parallel part plus the perpendicular part. I'll do two examples of how this works. Any questions about that yet?
Can you scroll up just a little bit?
Yeah. Ah. Okay, so need it more still?
No.
Okay, so the first one. So let's say that an object is moving in a path like this, and it's going this direction, and let's say it's speeding up. And we want to draw the acceleration vector. Okay, so first of all, the velocity vector is tangent to the path. So that could be this way is tangent and this way is tangent, but it has to be in the direction of motion, so it has to be that way. So that's the velocity vector. Now the parallel part of the velocity, the part that's parallel to this v, the object is speeding up, so the parallel part has to be in the same direction as the velocity. So there's a parallel. Now the third step, you have to think about which direction this is turning. We're going to draw a vector that's perpendicular to the velocity vector, so either that way or that way. Is it turning into the circle or this way? Into the circle. And so the perpendicular part, bless you, goes like this. And now the last thing we have to do is use the rules of vector addition to come up with the total acceleration. So remember, to add vectors, you put the tail of one at the head of the other one, and the resultant vector goes from the free tail to the free head. So I'll move this perpendicular one over to here. And then the total acceleration vector goes from the free tail to the free head. So that's the total acceleration, something in that direction. Yeah. This is basically what the whole lab this week is about, is doing these sketches approximating the acceleration. Okay, so let me do one more. So let's say you have an object going this direction, slowing down. And we want to sketch the acceleration. The velocity vector is tangent to the path in the direction of motion, so there's v. The object's slowing down, so the parallel part is opposite v. The object's turning into the circle, so the perpendicular part is this. And then to do the vector addition, you have to move the tail of one of them to the head of the other one. And then the total acceleration goes from the free tail to the free head, like that. So if you had an object in 2 dimensions that was only speeding up or slowing down, how does the acceleration vector relate to the velocity vector? If it's not turning at all, it's only speeding up or slowing down, what do you know about the acceleration? It's, well, yeah, and it's the parallel part that's non-zero. You know what I mean? So if something is not turning, it's only speeding up or slowing down, the acceleration has to be parallel to the velocity. And if it's only turning and not speeding up or slowing down, what can you say about the acceleration? It has to be perpendicular to the velocity. Yep. And that kind of stuff is going to be important when we start talking about circular motion. Okay, that's all. See you in lab.